first lecture, we discussed the spherical lenses, so let's now talk about the astigmatic lenses. What are the astigmatic lenses? If we say that the spherical lenses is a part of a sphere, but in this occasion, the spherical lens is a part from a glass cylinder. So if we have this glass rod, and then we sliced it from the middle, so we have two halves, then each half of them now is called a glass cylinder. So here is a glass cylinder. So it is the portion, or if the portion is cut parallel to its axis, then this segment is called a convex cylinder. But if it is molded from the surface outside, then it is called a concave cylinder. So here, if we have this cylinder, and we sliced this cylinder from here, and we cut it from the center, so the resultant segment here is called a convex cylinder. So we cut vertically parallel to its axis. On the other hand, if we molded a glass on the outside surface of the cylinder with the axis parallel to the molding will be parallel to the axis, then the resultant segment will be called a minus cylinder. So the plus cylinder or the convex cylinder has a convex surface, and the minus cylinder has a concave surface. So here are some examples of, here is the convex cylinder, and here is a minus cylinder. This is a convex cylinder, and this is a convex cylinder, and this is a minus cylinder. So by just notice, you can see that the cylinder has a refractive power at one surface, and there is no refractive power at the other surface. So this is called the plano-concave cylinder, because it has a concave surface and a plano surface. This is a plano-concave cylinder, has a concave surface and plano surface. And this is called a plano-convex cylinder. It has a convex surface and it has a plano surface. As you can see here, it has a convex surface and it has a plano surface. So cylindrical lenses are curved in the horizontal meridian, so they act as a spherical lens in the horizontal meridian. This is very important. And they are not curved in the vertical meridian, so they act as a parallel plate of glass, so it has zero vergence. So remember when we were talking about the vergence power of the lenses. So if we have here this lens, this is a convex cylindrical lens. This cylindrical lens has two meridians. This is the vertical meridian. So this is the axis of the cylinder. And this is the horizontal meridian of the cylinder. So if we have horizontal light rays hitting this lens, they will come to a focus. So this focus is formed by the horizontal rays. However, if the light rays passing into the vertical axis, which is parallel to the axis of the cylinder, these light rays will not come to a focus because the vertical axis will act as a parallel plate of glasses. So the light rays will emerge parallel and they will not come to a focus. Hence the principle of the cylinder, that the cylinder is making only a focus at one meridian only. So again, to repeat, the cylinder has no power along its axis as it acts as a parallel plate of glass, and the maximum power is 90 degrees from the axis. Either it is concave or convex. For example, here we have a convex cylinder. This is the axis of the convex cylinder, and this is the horizontal curved meridian of the convex cylinder. So at each time the horizontal rays will come to the horizontal meridian, they will be focused at a single point. Each time horizontal rays will pass through the horizontal meridian, they will make a single point. So the axis doesn't have any power, but only the horizontal meridian has the power. So the horizontal meridian here is convex, so it makes a real focus behind the lens. While in case of concave cylinder, the concave cylinder cause divergence of light rays so that their extension will come to a focus in front of the lens, and this only occur at one meridian, which is the horizontal meridian. However, the axis, which is the vertical meridian, has a function to act as a parallel plate of glass. So the maximum power is always 90 degrees from the axis. So here is the axis, and here is the, let's make the pointer. So here is the axis, and here is the meridian of power. So as you can see that the meridian of power is perpendicular to the axis. So the image of the point is formed by the cylinder as a focal line parallel to the axis. So as you can see here, again, as we said, this is the axis, and this is the curved meridian, which act as a convex lens. So it make a point. So each time the horizontal rays pass through this convex cylinder, it will make a point, and another point, and another point. As you can see here, a point and a point. The junction of all these points will make a line. This line is parallel to axis of the cylinder. So the line is parallel to the axis of the cylinder. However, the power is perpendicular to the axis of the cylinder. So here is the meridian of power. It is perpendicular to the axis of the cylinder, and this is the focal line, which is the focus of the cylindrical lens, which is parallel to the axis. So to summarize, the focus of the spherical lens is always a point, whereas the focus of the cylindrical lens is always a focal line. I hope that this concept is clear, because this will be the basis of all what we will see now in few minutes. So again, here is a cylindrical lens. It's a convex cylindrical lens. The convex cylindrical lens has an axis. This axis doesn't have any power and has a curved surface, which act as a spherical lens. This power, or this curved surface, will cause the rays to be convergent or divergent to a point. The junctions of these points will lead to a line. This is the focus of this cylinder. The cylinder will cause a focus into a focal line, not a focal point. This focal line is parallel to the axis. And the same thing occur with in case of the cylindrical minus lens. How can we do the notation of the cylindrical lens? So the spherical lens has only single notation by the power. So we can call that the spherical lens is +3, +4, -2, -3. But the cylindrical lens has two notations. The first one is the power. So 1 diopter of the power, meaning that the focal line is present at 1 meter. So as we mentioned in the last lecture, the dioptric power of a spherical lens, meaning that this lens make a focus at 1 meter, or the 1 diopter meaning that it will make a single point focus at 1 meter. But in case of a cylindrical lens, the 1 diopter will be equal a focal line at 1 meter. The new thing about the cylindrical lens that this focal line has an axis, and this axis also should be noted. And the famous notation for the axis is the TABO system, in which the right eye has the 180 degrees temporally and the 0 nasally. So the 0, 45, 90, 135, and 180. So you note where is the axis of the focal line of the cylinder. And the left eye will be started with the 0 from temporally to 180 nasally. The cylindrical lens has a variety of uses. So they can be used for refractive purposes. So they can be used for correction of regular astigmatism. And we have mentioned some of its rules in the last lecture when we were talking about the prism. We said that it has a use in Maddox rod test. So a Maddox rod test is a test used for measurement of the heterophoria, so we can know if this patient has latent squint or not, Also can be used for cyclodeviation. So we know that the patient has in cyclotorsion or excyclotorsion and other orthoptic exercises. So for example, we said that the Maddox rod is a series of high powerful plus cylinder. So every one of these is a plus cylinder. The plus cylinder is about plus 150 diopters of each cylinder. So these high plus cylinders, each one of these cylinders will make a single point. The single point, when joined together, will make a focal line. This focal line will be perpendicular to the direction of the axis. It will be parallel to the axis, and it will be perpendicular to the refractive meridian of these cylinders. So these cylinders has a vertical refractive meridian, and then so these vertical cylinders will cause horizontal line. So this patient who has these vertical cylinders will see a horizontal line. So in for this example, if this patient has a horizontal Maddox rod, he will see a vertical line. The base of this of this test is to dissociate the eye, both eyes. So one eye will see a line, and the other eye will see a white spot. If the patient is able to see that the white line, the white spot is coinciding with the red line, then this eye doesn't have heterophoria and this eye is orthophoric. The reverse occur if the lines are vertical. So if the cylinders are vertical, so this patient will see a horizontal line. And if the patient can see the white spot coinciding with the horizontal line, so this patient doesn't have heterophoria. Also, it can be used for measurement of the cyclodeviation. So by cyclodeviation, meaning that if the patient has in cyclotorsion or excyclotorsion, so both the cylinders are placed, or red Maddox rod is placed in front of the red eye, and a green Maddox rod is placed in front of the left eye, while the glass rods or the cylinders are in the horizontal direction. The patient will see a white or a vertical line. So if the patient can see the vertical lines of the both eyes parallel to each other, then this means that the patient doesn't have cyclodeviation. If they are oblique like this, so the patient has cyclodeviation. So we said that there is what's called a spherical lens, which has a refractive power at all its meridians, and we have the cylindrical lens, which has a refractive power in only one meridian. So what happens if we combine both lenses? If we combine both lenses together, this will be called a toric lens. A toric lens is a spherocylindrical lens. So this lens has both the radius of curvature of one meridian will be different from the radius of curvature of the perpendicular meridian. Again, the spherical lens has a regular and equal refractive power in all meridians. A cylindrical lens has only refractive power in single meridian, while the toric lens has refractive power in all meridians, but it has a meridian of highest curvature or highest power, and it has a meridian of the lowest power. So for example, let's say that this is Adam. Adam has no astigmatism, so he has a spherical cornea, and he doesn't suffer from any astigmatism. So he has the vertical meridian is equal to the horizontal meridian, and by vertical and horizontal we are referring to the main meridians. So we are referring to the meridian of the highest curvature and the meridian of lowest curvature. His father has astigmatism, and this astigmatism makes his vertical meridian more curved than his horizontal meridian. So since this, the cornea here is toric, meaning that it has a refractive power of two different meridians perpendicular to each other, with gradual transition in between these meridians. And this will lead to that this patient will have what is called with the rule astigmatism, in which the astigmatism is present on the vertical meridian only. His grandfather has also astigmatism, but this astigmatism is against the rule, meaning that what is meant by the against the rule astigmatism? It is the astigmatism in which the horizontal meridian is more curved than the vertical meridian. So here this is more powerful, or the horizontal meridian more powerful than the vertical meridian. So what will be the result of this toric cornea, or what will be the result of this astigmatism? So if we have a cornea which is spherical in shape, so that the power of all meridians of the cornea are the same. So every meridian of the cornea, like the vertical, like the horizontal, will cause refraction of light rays, and this refraction will cause convergence to be meet at a single focal point, which is present in the fovea, so this patient will see perfect 6/6 vision. However, this is not the case with astigmatism. So for the astigmatism, for example, if this patient has a normal meridian horizontal, so if the horizontal light rays will pass through this meridian and will be converged at the retina, because this is normal meridian. However, if the vertical meridian, which is the greenish one, pass through the vertical aspect, the vertical meridian of the cornea, they will be converged to a point in front of the retina. So the vertical power is different from the horizontal power. This leads to what's called astigmatism. So astigmatism, A, meaning that there is no stigma, meaning that point. So this patient cannot focus the image into a single point. So he has multiple focal points, and that's why this will lead to impaired or blurred vision at this patient. So to repeat the example, what we meant by a toric surface meaning that it is a surface that has different refractive power in the perpendicular meridian. So it has a meridian of greatest power, like here the horizontal meridian, causing the focus of the image in front of the retina, and it has also a meridian of lowest power, which will refract and converge the light rays behind the retina because it is a weak meridian. Again and again and again. In the spherical lens, it is a lens that has refractive power which is the same along its all meridian. So whether it is on the 90 degrees, or it is 180 degrees, or 135 or 45, whatever the light rays pass through any meridian, it will undergo the same refraction. So if we have here the optical axis, and this is the principal meridian, and this is the spherical refractive surface. If we have light rays passing through the vertical meridian, it will intersect into a single point. If we have a light rays passing into the horizontal meridian, it will intersect into the same single point. So both of them will intersect into the same single point, and this will cause a single point refraction. In case of a cylindrical lens, this cylindrical lens has a refractive power along one surface only, and it has no power over the perpendicular surface. So if the light ray is passing along the horizontal meridian, like this one, this will cause, it will act as a spherical lens. So it will cause refraction at a single point. Different or a refraction through the same horizontal meridian at different levels will cause different, or will cause multiple focal points. The junction of these focal points will cause a focal line, and this focal line will be parallel to the axis and perpendicular to the meridian of the horizontal power. If we have a toric lens, in case of toric lens, then we have the two main meridians have refractive power, but one great refractive power and one high refractive power, and the other is low refractive power. So for example, if we have the horizontal meridian here, it acts as a spherical lens, so it will cause it will converge the light rays into a single focus, leading to formation of a focal line, since this is a cylindrical lens. And by by the light rays passing into the vertical meridian will cause again another focal line. So the one refractive surface will cause a focal line, and the second refractive surface will cause a next or a second focal line, and the junction between both of them, both of the first focal line and the second focal line, will be called the interval of Sturm. So one of the most important questions in the cylindrical lens is the interval of Sturm. So let's have more information about it. Conoid of Sturm or interval of Sturm, it is a bundle of light refracted by an astigmatic optical system. So it is appear as a geometric envelope of light that is refracted by the toric lens, and it is elliptical in shape. So let's see an example. So we have here a toric lens, and this toric lens has a meridian of greatest curvature and meridian of least curvature. Here is the vertical meridian will cause a focal line. This is the focal line formed by the vertical meridian, and this is the focal line formed by the horizontal meridian. So the junction between the first focal line and the second focal line, this is called the conoid of Sturm. So what will the conoid of Sturm will consist of? So here we have the vertical lights will come to a focus here, and the yellowish line or yellowish meridian will come to a focus here. So the junction of the focus of the horizontal meridian and the vertical meridian will form a line which is called the first focal line or primary focal line. Then we have the focus of the secondary of the horizontal meridian, and the light from the vertical meridian will form a vertical light. So the vertical will cause vertical. So this will be called the secondary focal line, and the junction between the first and the second focal line will be called the conoid of Sturm. The center, the exact center of this conoid of Sturm is a circle. This circle where the vision is the maximum or the best, because the circle is very small, so it is well defined, and it is located between the converging rays of and the converging and diverging rays of the horizontal and the vertical meridian. This circle is called the circle of least confusion. So this is where the patient see the best. So the circle of least confusion is present at the center of conoid of Sturm, and it is the dioptric mid-value of the spherical lens and defined as the spherical equivalent of the lens. So we can calculate the power or the value of the circle of least confusion, as we will see later on, by calculating the spherical equivalent. To just imagine what does it look like, the circle of least confusion. So imagine that this is a toric lens, so it has a meridian of refractive power that is different from the horizontal meridian of another refractive power. So it will form a first focal line and a secondary focal line like this, and as you can see here that there is the vertical light make a point and conversion to a point, then it continue its pathway leading to divergence, and also the horizontal red light will make a point of convergence like here, and then it will also continue later on by the divergence. So the first one, or the focal line, which is made by the horizontal light, which will be the horizontal first focal line, this will be the image, and this will be the second image, or what will be the secondary focal line formed by the horizontal light, the focus of the horizontal light. So it will lead to, this is the secondary focal line. In this condition, whether if the image is present here or if the patient perceives the image here or here, there will be of poor quality. But the best quality if the patient see the image at the center of the conoid of Sturm, and this center will make the image rounded, and it will achieve the best vision possible with this toric surface. So this is called the circle of least confusion. So conoid of Sturm, it is the distance between the two focal lines, and it is the measure of astigmatism. And the correction of astigmatism is done by reducing these two focal lines into single focus. So, for example, if this patient, and now this toric lens will form a first focal line and a secondary focal line. So what does the patient see exactly? The patient doesn't see doesn't see the first focal line, and the patient doesn't see the circle of least confusion. But in this particular condition, the patient see the whole this from here to like there. So the image is distributed over large area of the retina. This will lead to that the image will be very blurred, and the horizon and the interval of Sturm is present from the first focal line to the second focal line, and here is the circle of least confusion. Our aim of refractive correction in case of astigmatism is to move the circle of least confusion to be on the retina. So when the circle of least confusion is moved on the retina, the image will be much more clear. However, it will not be the best, because again, it is still a circle of least confusion, and we want it to be a single point on the retina. So if the patient has the best toric correction, if the patient is corrected by the suitable spherocylindrical lens, this circle of least confusion will move onto the retina and will be converted into a single point, leading to very good vision. Another important topic is what will be the effect of lenses on the conoid of Sturm. So if we place this spherical or cylindrical lens, whether they are convex or concave, will they have any effect on the conoid of Sturm? Let's see. So suppose that this is the toric lens or the spherocylindrical lens, and this is the vertical, or this is the first focal line. This is the second focal line, and this is the circle of least confusion. So what will be the effect if we put lenses in front of the conoid of Sturm? First of all, let's put a convex lens. What will be the effect of convex lens? The convex lens will move the entire conoid of Sturm to the left. So it will move the entire conoid of Sturm toward the lens. Not only this, but also it will decrease the interval of Sturm. So it will decrease the size or the length of the conoid of Sturm. This will be the effect of the convex lens. So the reverse occur with the concave lens. So if we put a concave lens in front of conoid of Sturm, this will lead to displacement of the conoid of Sturm to the right, and it will lead to spacing, increase the space between the first focal line, second focal line, and the conoid and the circle of least confusion. So these are the effect of convex and concave lenses. What happens if we put a spherocylindrical lens? So if we put a toric lens or a spherocylindrical lens, it will affect the focal line parallel to its axis. Again, it will not have an effect over the whole focal lines. It will not affect the two focal lines, but it will only affect the focal line parallel to its axis. And it also affects the circle of least confusion. So again, our example here, this is the toric lens, and this is the first focal line, second focal line, and the circle of least confusion. And now we put a convex spherocylindrical lens. This convex spherocylindrical lens has its axis vertical. So what will be its effect? Yes, I think that you all know this. It will move the vertical focal line and the circle of least confusion toward the lens. So since it is convex or positive, it will move it toward the lens. But what shall it move actually? It will be the parallel focal line and the circle of least confusion. On the other hand, the effect of the concave cylindrical lens will cause moving the circle of least confusion and the parallel axis or parallel focal line away from the lens, and it will also move the circle of least confusion away from the lens.